All right, welcome everyone again. So today we're going to cover lecture number 3, processes. So last session we went over a brief history of computer architecture and major OS components, processes, threads, CPU scheduling, I/O management, and memory management, which again we're going to talk about in depth in the next lectures today. And lecture number 4 will be processes and threads. And then we also went over OS design approaches. So you should know all about these simple structure, layered microkernels, modular, their pros and cons, basically understand what are the differences between them, and be able to reason about them. Is there any questions regarding last session? By the way, even though I started recording, I'm going to ask, who found the history parts interesting? Just raise your hand. Okay, some people. Okay, because this is something that I introduced in the lectures, and I actually I'm looking for feedback. So if you have any feedback, send an email or let me know. I would appreciate it. Not just whining or nagging about anything, but actual feedback. All right. So today we're going to talk about processes, but before that, again, I'm just going to read over the assignments that we went last session. So introduction and Appendix A1 of Pinto's manual. So again, Pinto's manual. Yes, go ahead. Turn up the mic. Okay. This is actually as close as I can bring it up to my face, but. And the volume, I think I brought it up here. I'm going to try and then ask you if it's... Oh, there's also a program volume. Oh, no, that's program audio. I think it's this one. So the wireless microphone is at the highest now. Can you hear well or not? Oh, it might not be on? Really? Oh, yes. It is actually on, but the battery is dead. Dead battery, it says. Okay. Well... that's kind of unfortunate. All right, I'm going to try and speak a little bit louder. So that's at least, I know that I should do that first session. This was off and I didn't know. So thanks for telling me. All right. So again, the documentation, make sure you go over them because they have important information regarding understanding a bit on how the threads and project number 1 is there. Again, personally, when I took this course, I did not go over the manual of Pinto's till it was like kind of late, and then I was like, wow, there are so much useful information in there, and I was like trying my best to start from scratch or anything. So if it's still you're having issues with your VM, again, make sure you post it on Piazza or visit office hours, or at the worst case, just let me know. Again, we have tried to resolve a couple of students' issues. I saw a couple of related posts on Piazza as well, which is good. Again, if you posted earlier, the better. And so today we're going to talk about processes. The processes are very important, and for you to understand the differences between the process and threads, you'll understand again next session. But the concept is different than how it is implemented, for example, in your Pinto source code, right? So we talk about the representation of the process in OS. What is it? We're going to talk about how the processes get created or terminated, how a context switching is happening, and actually what is that. I will try to demonstrate it, and make it more clear. Process queues, we talked about them quickly or briefly last session. And a little bit about scheduling. Again, you'll have a lecture specifically, or 2 lectures actually, for schedulers and scheduling. So, but this is important again as a concept, what's happening in the OS, and how the processes communicate with each other. All right. So, if you remember last session, we went over that a process is it's a concept that is in a program in execution, right? So we talked about that there's nothing else than the CPU running instructions, right? But which instructions and to what purpose defines a process. So a process is a web server because this is put on this part of memory, and the purpose is to act as a web server to request and respond to the requests, right? Now again, the CPU just runs instructions and, can be interrupted, switch to the other processes, but it's just like, know that the process is not a, smart entity of its own. So a process now has three parts. One is the executable program itself, which are the instructions, which again meant to do or satisfy a purpose. An associated data needed by the program. Obviously, for making the pasta, you need, ingredients, whatever. And these are the user address in the user address space. The program itself, no matter what, it doesn't need to know what other programs are running on your OS, or at some point even what is the OS, right? That's the portability, right? So, but the program itself needs to access to these because this one wants to run. Now, there is another part of the process that the user cannot access, but the OS can, and that's the context of the process. So this context is the important information that the OS needs about the process. So, right, what is the ID of this process, right? How can it call this process? What is the name of it? What's the state of it? Is it like waiting? Is it blocked? Is it ready? These are the things, again, the processes need to know. The OS needs to know. And also the actual CPU context, which is the registers needed to run this process at the time, right? So as an example is the stack pointer, for example. Even the stack itself is put into the program does not have a direct access to its stack, but it just like uses it. So this is like a snapshot of this. So a process in memory takes some space, which again, the user thinks that this is the only thing that there is, and if it tries to violate that, OS catches it and stops it. Again, it has access to data and the program code itself. The context consists of PCB, which is a process control block, and it's a stack, which again it just uses during the execution, right? And so the PCB is a snapshot of information that needed for that process, right? Basically, it defines the process when you look at it as an observer, right? You can read those and then say, okay, here it is. This is the state of it, and and then this is there's a process table in the operating system that basically holds all the information about all the processes. That then it has links to the process blocks one by one. It might be an array, it might be a linked list, but basically the OS can tell what is the first process, what is the second process, how can I find the next one, and then basically can reach out to any of these PCBs to find the information about each process. All right. So now looking a little bit more, in depth. This is again an illustration of your memory, and so some part of it is obviously your OS itself. Some part of them, each of them, like it's a different process. Within each process, we just showed that there is a context and then there's user address space. Now the context itself is PCB and stack. So process control block, the stack, you already know what's going on in it, right? You just push and pop from it the information needed when you call a function, return from a function, and so on. Now the process control block holds information such as the identification of the process, CPU state info of the process, and control info, right? So identification is what is this? What process is this? It has an identifier, which is like usually a unique number, process number 1048. A parent identifier, who's the parent of this process? Like which process made this process, right? And then user identifier, again, these are some just I think that's like says who owns this as, for example, user access and privileges. CPU state info, which is again important at the runtime. These are registers of the CPU, like flags, control, program counter, and stack pointer. So the CPU use this during runtime. And this is, again, very important. We try to make it clear today. Control info is the schedule and state info. For example, when the OS looks at it, should I schedule this next, or is it like waiting for an I/O, right? Is it in a queue? What are the memory limits of this, right? So, for example, if OS wants to basically load this information. It needs this to set the CPU. So for when this process wants to access this memory address, right, there should be a trap. Hey, your memory is limited, defined by these numbers, so you can't access past this point, right? So these information are there. So if a process wants to open a file, or read from a file which does not have access, or it doesn't have it opened, again, the OS can take a look at these and say, oh, you haven't opened this file, so you should not have an access to this, so no. All right? So the state of the process can change during execution. When a process is created, it's in the new phase of it. Like it's a newborn process, and then it's trying to, the OS tries to shape it and, put it on the memory in the right space. And then after that, it will be in the ready state, meaning this process is ready to be scheduled, right? Maybe it's not yet there yet, maybe it takes some time, but at least the OS knows who is ready. One process at a time can be running. Again, we're talking about a single core. So one process at a time is running, and their instructions are being executed. And then basically they'll move between queues. So one from ready goes to running. And then depending on the state, the running process can be waiting. For example, if you're waiting for an I/O, waiting for an interrupt, all those cases, the process should be waiting. They're not ready yet to be scheduled, because if you schedule them, they'll say, okay, where's my information, right? So they're not technically ready. And once they're done, they will turn into a terminated. There are, again, things that the OS needs to do with a terminated process. It's not that they're just gone, no. So this is a diagram. They get admitted and then go to ready queue. Once they are scheduled, the scheduler dispatches them to the running state, and then they keep running, and then there are 3 ways to go. If an interrupt comes, they go back to ready queue because they were running, they just were forcibly stopped. If they have an I/O request of their own, they will probably go back to like an I/O queue and then wait for the OS to be done with that I/O or event that they're waiting for, and then they will go back to ready. Maybe they get back to running state immediately, maybe not. And then once they're done, they get terminated, right? Any question? All right. So during a process creation, there are things that can happen. So first of all, when your operating system boots, there's only one process that boots it, right? The loader brings they call it init, and this is like an initializer that just like boots every driver and then basically boots the kernel, right? That would be it. But then that would spawn new processes, right? So for example, other daemons, services, network services, all the things that the system programs log on, right? These are even before a user wants to do anything, the system just like spawns them, and these are now different processes. So that's just like what happens. Now a user themselves can request to run an application, right? Meaning when you run in your bash script, hey, when you double click on something, right? That's a user application or user itself that wants to run it. So that goes through a different process. Right. So, for example, when you double click on an icon or wants to run it, then you are telling your OS that, hey, I want to run this executable, so spawn a new process. Or when you run a shell, the shell itself is a program, right? But then it tells the OS that, hey, I want, because the user has asked me, but it doesn't matter. Now I want to spawn a new process, whatever it is, right? So this is another one. And an existing process spawns a child process by itself, right? Maybe during execution, that's how it is defined. So, a web server, for example, we'll get to it in also next session. But, if they want to do it, they can. Like, if I need more, processes, then I'll just create it without, someone asking me. I'm asking it. And then basically, this is one case, for example, that the init daemon waits for user login and spawns a shell. This is a case, for example, when you open up a computer into command line. So that init process of when you boot, it's waiting for the user login process, and then it opens a shell. Again, it spawns a process without you asking it. And like a batch system that has processes after another ready in the queue. Once the one job is done, then it starts another process. All right? Is the voice clear, or I should go louder? All right. So this is a tree of processes in a typical Unix system. You start with the root process, and then it basically spawns in it. It's a daemon itself, which then handles all the services and everything. And then there's the swapper, and then page daemon. These are to manage your virtual memory, and then again everything just grows. All right. So before going to that, how this process happens, how a process can spawn another process is called fork, right? And before diving into it in the next page, I want to actually show it on on a piece of blackboard. And because this fork is really important for you to understand. Oh, and now I see that this should be on. No, this one. Oh, okay, yes, this was missing. So a fork is called fork, right? It's a function. So it's a system call, which means a process asks operating system to do something for it. That's a system call, right? And we're gonna have it, demonstrated like this. So if I am a process, right? Well, today I'm going to be many things. I'm going to be CPU, I'm going to be OS, I'm going to be a process. But let's say a running process instructions are here, right? And I'm the CPU, right? The CPU only runs one thing at a time, right? So I am running these instructions, which again is part of a program, right? So the program has decided, meaning it's as part of execution, tells the CPU, or has it, that put this paper on table. This table you'll deal with in your project too, right? So the CPU is running these, and then basically we'll take this paper from here and then put it on the table, right? That's it. And then the next instruction in the program is ring the bell. This is the bell for OS, right? So the CPU basically, when runs this ring the bell, it's just like a ding. It's a very specific kind of instruction. It's a software interrupt, meaning when it executes, it's as if an interrupt has happened. What does an interrupt do? It pauses the current process and then calls the operating system, right? Now, operating system code is a different place, right? We know the kernel code, for example, might be here. Now, the kernel first checks what is the cause, right? Why are you reading me right now, right? What is the state? So the CPU, the state of the computer is that the ring has, someone has rang the bell, right? The operating system knows what to do with the bell, right? Is it the bell? Then that means someone has a request from me. What I need to do? I need to look at the table, right? So the OS code is now look at the table and then see what's going on, right? Then as an OS, this code is now running in the OS mode and privileges. I'm going to take a look at this, right? I'm going to read it. So who was previously running, first of all? I can see that as an OS. Who was running, when the interrupt came? Oh, actually, I did bring them up here. So I have like some colored papers, which are hopefully going to help. So when a process is running, it's going to be on this, right? So the OS can say, oh, this is the, the process blue is running, and so what does it need? It needs to open a file, it needs to fork or whatever. Now, as an OS, I will first check, do you have, is your request valid? Do you have the privileges? Are you giving me valid information? If so, I'm going to do this for you, because I, as an OS, have access to all the memory, which you don't have, and I also have privileges that you don't have. So I'm going to create a process here, which was not there, and then copy you, all of you, into this. Well, except the process control block. It's going to be similar to this, but not exactly. And the process block actually is, yeah. But the code and data, all of it, will be copied into this. This is very important during the fork. That's the only thing that the OS does, apart from giving you a feedback. How is that? So this is a general system call. Now, in the case of a fork system call, it's a function. What does the function have? A return value, right? So if you call a function, you can get this and put it into like a, return fork value. It's a variable, right? So when you call this function, I already know that you're asking for it. So I, as an OS, will put a value inside the stack of your, stack. And that also, again, because you copied a process, that's also going to be here. This is important because this, I don't have, actually I do. This will be different. Okay? So this is a fork. So now I copy this process, I create the process, I copy everything from this except their, PCB will be different. And then I, as an OS, will be, okay, I'm done with fork because that was fork, so return. What does the CPU do when it returns? It just goes back to whatever it was doing. What am I doing? I'm running process blue. What is the process blue? Oh, I should have also put this one here. This is process blue, right? So it just goes back to where I was in the program counter in the middle right here, and then it just continues running the instructions. That's what exactly is happening. Now it is very important because at this point, this process does not have any access to this process anymore, right? So if I want, if this is the shell and it wants to open a PDF reader, that's a different program, right? How can I have this be a PDF reader? Any guess? I mean, it would be difficult. Fork is really almost most complicated thing in the process concept. Remember, this is a process. At some point, this will get scheduled by itself, right? Now, remember that this is very similar to this. The code in here will be this. Actually, when it gets scheduled, because this was exactly like this, right? This doesn't hold. So because this was very similar to this, the context is also very similar. So when the OS schedules this, and the CPU wants to take a look at, okay, what instruction I should run, where it goes to? Where it goes to in this instruction? Come on, make a guess. Huh? The pink one. It goes to the pink one. But this pink one has a whole execution of this, right? There are all thousands of instructions. Which instruction the CPU runs first? Huh? Which one?
The highest priority.
No, and not the first one. Again, remember, this was a copy of this. Very exactly left off on this one. So although there are thousands of instructions, and these instructions are exactly like this, but because it's resuming it, it will resume it because this was also a copy of this. So when the CPU looks at this, it says that I was in the middle of it. So it actually starts from right here, right after the bell. It's as if this process also rang a bell. Right? So even though this program at this point cannot affect this program, but if it has it in its execution flow, this program run that by itself, right? So there is no need actually for this to do something for another process. This can write it here to run itself. Like it can say, replace me, right? And the OS then replace this code instead of a shell with a PDF viewer, right? Because this is like itself. It can access itself. Yes?
So if this one is a copy of this one is no longer useful?
No, it is. It is. It's a copy. So either of them can get scheduled. And the key point is here. If you put replace me here in the code, that means this replace me was also here, right? Replace. So is this also going to be a PDF reader? Well, yes. If you just put it as is, it's going to do that. How can you differentiate it? How can you do it only in one of them? So basically, you want a piece of code that runs sometimes but not other times. What is that? An if statement, right? And I just said that these processes are very similar except one thing. They're in PCB, but remember the process themselves cannot access their PCB. So the if statement, the condition variable, is something that the processes still can access. What is that? What's that? ID? This one, right? This is what I said. When the OS does it, just for the sake of this, so the process can differentiate itself with its clone, or basically from its parent, right? This is the only thing, and that's the return of the fork. Okay? So then basically you can have an if statement. We're going to actually show up in this slide. So then in that if statement, you can basically just separate the whole flow. If I am still me, am I the original one? Just continue the flow. Am I the new one? Then open up a PDF reader. Do it something else. That's the usual case of a process. Now this replace me is an exec-v, and that's we're going to go over that. All right? So I'm going to put these back. Was that clear? Is there any question for that? This is very important. The return value of the fork basically differentiates a process from another one. That's the only difference between them in terms of the user execution. Yes?
How do you return back to the original if you continue to make more of the clones? Go back to the first?
Well, it returns to the next instruction. So when you call the fork is an instruction, right? That's an interrupt. When you resume, meaning the OS now schedules you back, you basically resume to the next instruction. So you don't keep calling fork, unless you want to. But if you call it only once, that gets only run once. We have an example of running multiple forks. All right? Yeah. Yes?
So you're creating a process, and then from like the original process, right? And that's just when an interrupt happens, and then you return to the original process, and the other one gets deleted.
No.
So
what was the first part of your question? You said that this gets cloned and then?
Yeah, it gets cloned. So like after, because there's a return value.
Yep.
It just comes back to the original process.
Yes, this function returns to this line, the next line.
So what happens to the other one?
The other one, again, because it's a copy, it's as if it is a process in the middle of its execution that has called fork. It's exactly in the same state as this one. So remember, the OS at intervals schedules different processes. Once it schedules this process, now says here, this process is ready to run, and then go ahead and run, this process thinks that I was running, and then I called fork, and now here is, I returned. How does it know if it was the case or not? That's just what I said. If it looks at this value that the fork returned, it can tell, okay, if I did even existed like a moment before this, or was it actually just created, right? So we will see this in example in the code in the next slide, right?
Professor,
Yeah.
clones persist after.
Basically this process is called the parent of this process. The relationship between a parent and child is, can be defined. So if a parent terminates first, what happens to the child? If a child, if a parent wants to wait for it, we have like orphaned and zombie processes. We're going to talk about them briefly today, but this is like a different thing, all right, so let's see. So this code, basically, the rest of the code is not important, but when you call fork and then return the value in this PID, this instruction itself returns 2 times. Fork is a function that basically is called once, but is returned 2 times. Basically, it doesn't return to the same process. It returns to 2 processes, right? So when the difference that I said that there are 2 different values, but what are the values? When a process gets created, it has an ID, right? Process ID. And so for a parent process, which was the original process here, right? The fork returns the process ID of the child. When the OS creates the child, it assigns it a process ID, right? It returns that value to the fork of the parent process. What does it return to the process of the child? Huh? Just make a guess.
Its own parent ID?
Its own, well, not parent ID.
Well, because if in case it makes another child, then would it itself be a parent ID of the child?
Well, no. Remember, the child does not know yet that it's a child.
Oh, okay.
So if you give it any number, how does it know that that's the number of my child or me? Think of it. It should be a special number. 0. 0. Because no PID is 0. No process ID is 0. Right? The init or the root process ID of the OS is 1. It starts with 1. So 0 is the special case that will be returned to the child. So if the child checks it, in the execution of both of them, basically it runs. Is it 0? If this statement returns true, basically that means, oh, I am the child. Someone created me right here. And now I'm executing. So what do I want to do? Well, I want to run the command. This is the actual child process replace me, right? So this command will not return. These two commands are very, special. The fork calls once, returns twice. Execvp never returns because it says replace me with this command. So it's not like going to read any of these. It's going to go to a PDF reader. It's going to go do something else. So it's never going to come back, right? So that's a law of what is this? Thermodynamic law. What is the conservation of returns and calls? So one has the 2 returns, the other one doesn't return. Okay. So, but if it's the parent, it does not have a 0. It has the child process ID, so it goes to the else and then basically does this, right? So in this execution, as an example, remember the first process runs, and then at the fork, the process has paused because it's a system call. Now the OS comes. The OS comes and opens up another memory space, copies the whole code, just changes the return value of the fork and return to both of them. Which one first? We don't know. That's the job of the scheduler. Both of them can be resumed at any point, right? Now we assume that first the child is going to run. So if the child resumes from this call function, it receives a 0. And then it checks it. Is it 0? Yes. So then it prints out, this is the child, and the PID of me is get PID. So even though the return value of the fork is 0, but each process can access its own ID using the get PID. It's also another system call. It cannot access PCB directly, but it asks the OS, what is my PID? Tell me, and the OS puts it in the return value. That's, but remember, by just executing PID, you cannot know if you are a child or not, unless you have saved it beforehand. So you have your parent PID in a variable here, and then you get your PID here, and then compare them. If they're still equal, that means you are a parent. If they're not equal, you are the child, right? Does that make sense? Right? So this line gets only run by the child itself, and the return value of the fork is 0, but it will call the get PID so that it prints out its own PID, and then just goes to execvp command. This command only returns, I said that it never returns, that's in the case of a successful. So if you want a PDF reader and there is no PDF reader, then obviously it's just going to return to an error, right? Then it should be handled basically, and then you terminate, because the child's purpose was to run something which doesn't exist, so it terminates. That's an example. And the parent process, if it resumes, it checks the PID, and the PID is not 0, so it is greater than 0, which is the process ID of the child. But it is now the parent who is running these. We are in the parent process. We print out my parent PID is the get PID, and my child PID is PID if it wants to print out that. And then this line is also waiting for a child. This is something that you ask about it. So a parent process can wait on their children because the reason is it's just like how it is defined. Why do we have like parent and child? Well, the parent process was a process that decided that I want another process, right? So maybe it wants to wait for that to finish. Maybe it wants, that child process to do something and then, continue. So that's why parents can wait on their children. Basically, you can't wait on other processes, in general. But normally, you don't wait on someone you don't know, right? So any questions for any of these? Fork and execvp, they're important to know and implement later on. Yes?
The fork is basically returning the process ID of the child
Mm-hmm.
to the parent and returns it to the child as well. That's basically the purpose of the fork.
Well, the purpose of a fork is to create a new process. That's one way to create a new process. When a process wants to create a separate process, right?
If you was to define a fork, how would you?
A fork is a system call that, when run, it creates a new process, clones the current executing process, data and execution with slight differences, and returns to two processes execution, basically.
So for this example in specific, we're waiting for the child process to terminate, right?
Yes, in this case, this process will go and get blocked until the other process gets finished.
But it doesn't necessarily have to do that. Like it depends on what you
What's that?
want to do. So if we want the other process to run simultaneously.
Yeah. There's no need to. There are, in this case, the ellipses are not here. Maybe they will be here. Maybe you run a lot of things, but in the end, before termination, you still want to make sure that my child is done. Because in some cases, parents can take their children with them down, right? All right. So we're gonna plow ahead a little bit. So this is a process creation. You clone the child process with fork, and that tells the OS to create a second, process completely with very similar context. Remember the identifiers, and some of them have different values. A lot of them will be the same. The data and the program obviously are clearly the same. And that return value, again, remember, that's in the stack, right? So that's the return value of the function. So that will be in the context. And then the rest of the execution of this, if it calls the execvp with the name of a program, then that will basically replace its data and program, and as well as the context, some part of the context, to the program number 2, right? Because that program is a complete program. So you're telling OS that load that up completely. So the ID might not change, but there are definitely open files, resources, a lot of things can change even in the context. All right. So this is an example of this. So if we have a return from fork and my PID is the get PID. Who am I basically? You call this at this point you have only one process. So let's say we have process ID number 56, right? And so this my PID gets 56, and then before my PID is 56, right? This is what you print out on the screen. Now, return from fork is a fork. At this point, you call the fork, you make this twice. Remember, both there are independent processes with the same data, meaning in both of them, there is a my PID which has been already valued 56, right? Now you return to both of them. You wait for a second in both of them, and then printf. After my fork returns PID, this said this. Return from fork and get PID. So this now, I'm going to write down on. Can everyone see this part of the board? Okay. So at first, I'm going to hold it actually, yeah. It's difficult. All right. So at first we have a 56, printed that out, and it says also before. Oh, this is not going to be good. All right. I'm going to put it up and then bring it down again, right? Because I can see it from here. Okay. So it says before my PID is 56, right? This gets printed once. And then you call fork, and now let's assume the child process's ID is 84, right? This is 56, this is 84 for some reason, right? I have nothing against other numbers. So then the second says like after my fork returns the return value, and then you also have the get PID. So there are now two cases. If the parent runs first, the parent process will print out after fork it returns 84 because that's the value that the fork returns. That's the child process ID. And then the get PID, which is again 56. The child runs the same line, and then now this is the child printing this. All will be in the same output screen, but now this is written by child. It says after, what is the return value of the fork in the child? 0. What is the get PID when the child calls it? 84. Now, depending on the scheduler, if the parent gets scheduled first or the child, these two lines can be printed out in different orders. But basically, this will get printed by the parent, this will get printed by the child. All right? So, going forward. So this is another example which calls multiple forks, right? So the question is, how many lines of output will this produce, this code? Quickly think about it and make a guess. These will get tricky. There are some of your exercises or questions which are similar to these, right? And most of them you assume the forks are all successful. There's no problem with running them, and then go ahead. So I'm gonna put this up and then solve it together here. All right. So let's see. You have a process. Let's call them for the starting from the 100. So you have process number 100, which then calls fork, right? It calls the fork number 1. We call them fork number 1, 2, and 3, right? When it calls fork number 1, what happens is that it generates another process, right? It creates this one. Now this one does not. It's as if it is finished with fork number 1. So it doesn't. So we call it like 101. So then both of them have fork number 2 in their execution flow. So that means this calls fork number 2 and generates another one, which is 102. And then this one also calls fork number 2, which that means it generates another one, which we call 103. In each of them, we are at the end of fork number 2. And all the processes, they have the execution of fork number 3 in them. So this runs fork number 3, and then it basically generates another one, which is like 104. And then this runs another, it doesn't matter, the order doesn't matter, right? So this runs fork number 3, which then generates 105. And then this runs another fork, which is fork number 3, which then generates 106. And then this runs at, finally, we don't have much space, 107. So basically, that would be 8 processes. Okay? So running a fork in a loop actually is something that just crashes your system immediately because it's just like it's, right? That was actually one of the first, one way actually to crash your system. I don't know if still OSs can figure that out, or they get tricked. All right? Any question in this? Yes. What's that? Lines? Oh, well, the end after the end of the fork, each of them will says my PID is get PID, right? So basically, now depending on which one of them gets scheduled first, after the third fork, all of them they have a print, right? Print, and each of them will basically print out their PID. So from 100 to 107, these 8 numbers get printed out with different orders. That's like 8 factorial different orders, possible orders, right? That's, I don't know, huge. Okay? So then, yeah, those numbers those are the lines. Okay? So next, we're going to show, I'm going to show you an exercise. So in the code below, assume that all forks and exec VPs are running successfully, and there's no error or something. And then the program arguments do not spawn more processes or print out any more characters. So that PDF reader doesn't do anything that we care now or print out anything. And then basically we want to see all the PID variables are initialized to 0. These are the and then what are the number of processes that will be created, and how many of each of the characters will be printed out. So this is the code, right? So just because of the space, just continue here and then come back, okay? So this code, take a look at it. It has like fork, exec VP here, fork, another fork here, a fork, and exec VP here, and another fork, right? So the solution actually will be in the next page. We're going to just go over the next slides, but if we get time, I'm going to go back to this. Otherwise, we'll have time later. But overall, just the same thing that I just showed you here, you have to draw that, but have it clear. Because in each process, you want to have it assigned a PID. It can be random, obviously. Remember that the order does not matter. In each of them, if there is a value in the parent process, that value stays the same in the child process. The only thing is the return value of the fork. So the PID number 1 after this call will be different between the parent and child, right? So this is a diagram that this type of questions you should have, right? So what I did here, you can have it in your draft and whatever, but it clears here how to do it. So this is the actual process, initial process. When you run it at fork number 1, this is the process that gets generated. Because it's a child, the P1 will be 0 in this, but the P1 in this will be something greater than 0. It doesn't matter, you don't have to assign it an actual number, but it will be greater than the 0. Now when it calls the fork number 2, because P1 was greater than the 0 in this, the P1 will also be greater than the 0 in this. But because P2 is a child return of this fork, this will be 0 in here, but greater than the 0 here. Now fork 2 also gets run on this, but because P1 is 0 in this, P1 also stays 0 in this, right? And then continuing with the execution flow, you will realize how these if statements can basically divert, and then some of them might print out letters, some of them might not, some of them might actually end up terminating and going to a separate program, whatever, right? We'll come back to this hopefully. And then now the termination. There are events that can happen and then terminate a program. For example, if one is just like finished, then it will call the OS and hey, I'm done. Just like wipe after me, clean up. The fatal error. If you try to access a memory, or if you are division by 0 or something. If you do not catch the error, or there's just segmentation fault or something that you're not supposed to have, then it will be terminated. OS intervenes. Close out. Or if a total time limit, if this process was to run for at most 2 seconds, if the 2 second mark is done, the OS just finishes. And if it's killed by another process, sometimes the parents will take down their children, right? When they're done, say, okay, I'm done, let's go to Neverland. The process receives a sick kill signal as well. So if a process wants to kill another signal, for example, when you call Control C, right? Your shell is not finished to take down its child process, but it wants to terminate its child process. That's how it. All right. Pauses and dispatches. There are things that can pause a process and then continue. So, for example, when you have an I/O wait, right? So this is through the system call. If a process tells the OS, hey, I have a request, and that request through the table, you remember, and that request is that I want to read some file from readme.txt. So the OS says, okay, I'm going to bring that from hard drive, but within the time that these information are getting retrieved from the hard drive, you don't want to, you don't have anything to do, right? So I'm just going to schedule other, processes while you wait. This is voluntary, basically. They're waiting. There are preemptive timeouts, so hardware interrupts. Maybe a process doesn't want to be paused, but it's just like a timer. Remember, the timer just ticks every now and often, and that tick just wakes the OS, pauses the CPU from whatever it was doing. If it was running this the process, when the timer ticks, the CPU know what to do. It pauses this process, goes to the OS code. I don't know what is that code, but it might not come back to the execution, right? So this is involuntary. And then in this case, because the process is basically ready, it was just running, so it's ready. The OS put it back to ready, not into waiting. It's not waiting for anything. It can be immediately scheduled, right? And now the context switching. This is also very important in terms of understanding how a CPU is like switching between different processes and resumes as if nothing has happened, right? So we're going to go over it quickly first. When you switch it, the system must save the state of the old process and then load the saved state of a previous one, right? So at any given time, all the other processes have their state saved. So when a process wants to resume them, it just loads them and continues. All the processes are always continuing, right? If you think of a process that gets started, there is no start. They're continuing, but they're continuing at the start of execution process flow, right? And the context switching is the overhead. The system is not doing any useful work. Meaning, if you have like multiple processes, one is the word editor, one is the game, whatever. When you are, switching between them so fast, within that context switch, it's the OS, like handling this, putting this, and this is not useful work. The actual work is done by the processes, right? So this is called overhead, and you have to minimize that, okay? And the time also, depending on the hardware support, it can happen fast or slow, all right? So the context switch, you might not actually read the code in Pintos because that's very elegant. I actually made a story when I was a TA. I will probably put it up. But it's at the end, it's happening a trick to the CPU in assembly code. But just remember that it's resuming to the other state. So this is the case. You have two processes, process 0, process 1. It's as if like it's executing. The CPU right here pauses or interrupts, for example, or system call. It goes to the operating system code. It saves this state into the PCB, and then reloads the state from a PCB of the process number 1, and then continues, and then just like runs the sys. Again, an interrupt or system call, and this happens. Again, it saves the state of this process, and then loads the state of this process, and this reloading is the exact thing that was saved here. So when it returns to this process, it's as if nothing has happened here, right? It just like continues. And remember, during the execution of operating system, all these PCBs and everything is like data. All the processes are just like data. They're just objects, right? So that's why this can happen. And this is the step-by-step things that are happening. The save the CPU context, including program counter and registers. This basically tells the stack, flags, whatever, and basically ensures the continuing execution. It's as if nothing has happened. The program counter allows to continue where it exactly left off, right? If it was running at this execution instruction, and then the next instruction is now saved. So when it wants to resume, it just continues at the next exact line, right? It updates the PCB. For example, the ready or blocked or something, the OS does this. If it looks at, okay, what has happened? If it's the timer, now I gotta look. Do I have to put this process away? Should I put it back in queue? Is it ready? Or has it called an I/O? So then the OS takes that process and put it in a right queue. Move the PCB to the queue, and then select another process for execution. It runs the algorithm for the scheduler and says, okay, who is now to be scheduled? Is it just next one? Is it the other one? Which one is waiting? And then that will update the PCB from that, changes the state of the other process to running now, and then just continues with running that. Any questions on this? Yes?
So is that all this stuff right here, is that all overhead then?
What? These are all overhead. Yes. These are all overhead. Yes. Because none of this has anything to do with either process 1 or 2, right? So no one cares. So what events trigger the OS to switch processes? There are interrupts. We said external interrupts like timer. They are happening asynchronously. You don't know when they're coming. And basically, they can be clock. It can be I/O, like a packet is coming, or a click is happening on the mouse or something. It can be a memory fault that, again, it was not. It's involuntary. So if a process wants to access to a part of the memory that it should have access, but it's just like not ready, then it should just, it's an interrupt, the OS handles it, and then the program doesn't know, it just doesn't expect. The synchronous events are, for example, exceptions. If you divide two numbers, you are running it. The process is responsible for running that division, but it might trap because it might be a division by 0, right? Now you can catch it, or if you don't do that, the OS will terminate it. So, but this is voluntary. System calls the exceptions are involuntary because you're not expecting it, the division by 0, but you are doing it, so you can catch them. And the system calls are voluntary. You call the OS, hey, I want this request, and now put me back in pause and handle this. And then the OS, once done, they can immediately resume the same, or just depending on the request, can put them in waiting or ready queue. All right.
What do you mean by traps?
So they're called traps. That's what they call. They're like software interrupts. There's an instruction that causes the CPU. It's as if an interrupt has happened, so it will automatically runs to a different part of the memory and then start executing, which the OS code supposedly is there, right? But it's voluntary. You call it. All right. So there are process queues. This is important for your project number 1. So you have a queue for all your tasks, and then you have the ready queue, which is the queue which are for the processes that are ready to be scheduled next. And then there are device queues, for example. So this is just 3 queues. They're not all queues. Depends on the implementation. But well, this has all of them, right? But besides that, a process is either ready or running or waiting for something, right? This can't be 2 of these, right? So that's why we say the processes migrate among them. So if it's running, then it goes to the ready. Now, if it's waiting for an I/O, it should not be in the ready queue anymore. It will go into another queue, right? Because you don't want the scheduler to schedule it again until that thing happens. When that thing happens, the OS should bring it back. All right? So this is, for example, again, some queues. You have blocked. So if all of these processes are waiting for something, then when that thing happens, the OS gets to know through interrupts, right? Then it will come to those blocks and see, okay, which one is first to wake up. Then I will put you back into ready, right? So this is the queues. Last session we also talked about them. This is, for example, all of these are waiting for disk. They should not get scheduled. They're not in the ready mode. Once the disk is done, then this process can move back to the ready queue. And again, this is a representation of processes scheduling. The CPU is running, and then it can go to ready queue for different reasons. So if a time slice is expired, another process should come and get scheduled. The OS just puts it back in ready, just as that. Now, if an I/O request is in the execution, so then it will go to the I/O queue. Once that I/O is done, the OS brings it back to ready queue. If forks a child, the child gets created, and basically both of these processes will get back to ready queue. Each of them can get resumed. If they wait for an interrupt, then they will get blocked and not in the ready queue until that interrupt happens. Then they will get migrated from that to the ready queue. All right. So, and then we have this is a different aspect of scheduling. This is not the necessarily process scheduling, but we have different types of scheduling. So when you have many processes running in the main memory, then you have the CPU scheduler, which is in short term, quickly scheduling back and forth other processes. We have a long-term scheduler. So this is not a case in your operating systems, but for example, a batch system, right? Every now and often, if there are 5 processes running here and a process gets done and terminated, then it will get the next process and bring it here, right? But this happens at much lower frequency, right? Every time a process is finishing, it brings the next one. So it's called a long term. And what we have here also is a midterm, because although these processes might be running, but maybe they're not getting scheduled for some reason, and they're just taking space here. So at intervals, they will be taken to the disk, swapped out, and then when they are ready for some reason, they get back swapped in. This is also midterm. So the frequency gets higher when in the short term rather than long term, and also the granularity is changing. So this is, again, the long term is just like a decision which programs to be pulled in the memory. The short term memory, which is the CPU scheduling and what we're talking about, is the decision of which of the processes in the ready queue should be scheduled now, and this is called dispatching, or again, CPU scheduling. The medium term is something, for example, again, as the example in swapping. Again, a process might be there on the memory right now, but it's just like not running at the moment. So it's just like taking space. You swap it out, and then you swap it back in, right? And so it's important why we're talking about this. So short-term schedulers are happening, at milliseconds, must be fast. The scheduling process should be very fast because it's just overhead, right? If the 10% of work is just overhead, you're using only 90% of your CPU availability. The long term can take, slow, so it can be slower. And this controls the degree of multi-programming. That means, again, if you have 5 processes running at the same time, then this is the long-term scheduler that handles. If 5 is enough, if not, I can take another, from the batch in. Now I have 6. Now, if one gets out, it gets 4. So should I wait for or bring another one? So basically, this defines how many processes are there at the moment. That's what we mean by multi-programming. And then, so this is what is important with the long-term and midterm schedulers. The processes are described either as I/O bound or CPU bound, right? What does it mean? So a calculation process, which only does calculation, right? It's CPU bound because its execution is bound to this, a CPU time that is being given. Whereas a word editor doesn't do anything until you click something, right? For example, a simple one. So although it is there, it's not doing anything. It's not running anything until the interrupt comes. Or, if it's writing something on the hard drive, it will, read a bit, write a bit, and then waits for the hard drive. So the CPU is doing nothing. So it's important now to have a balance between them. So the scheduler should be smart. If only you schedule the I/O bound processes, then the CPU is not doing anything. It's only waiting on the I/Os. If you only do this one, then you're not utilizing your I/O, right? Maybe a process only wants to send a packet, but you're not scheduling it for no reason, right? So this is important when you are thinking about scheduling. And then we have, again, the midterm schedulers, which are for swapping out, and swapping in when the processes that are currently in memory. So then we have cooperating processes, which is the intercommunication between the processes. So processes can cooperate for different reasons: information sharing, computation speed up, modularity, and convenience. And it's really difficult because the disadvantage is synchronization. If 2 processes want to work with each other, how can they communicate and then say, okay, you do this first, and then I will do this? Or if we want to share same piece of information. So inter-process communication will happen in 2 different ways. One is shared memory, and one is message passing. If you have a shared memory and then the 2 processes are using that information, and they have access to it, this is one way to communicate. You only have to avoid race conditions that 2 at the same time want to modify something. And they can also message pass. They can not have a shared, but they can ask OS to send this message to the other process, or get me a message if I have from other processes. So this is the analogy. So the shared memory, they can both access. The message passing, they ask OS to do this for them. So message passing facility provides 2 operations, either send or receive. And if P and Q wish to communicate, they need to have a link between them, right? They cannot just so that link should be there. They have to establish it first. And then the send and receive are the ways to do that. And these are concepts. The implementation can vary in operating systems. And then we have direct communication and indirect. What does it mean? The direct communication is that they say, hey, I want to send a message to P, and then I want to receive a message exactly from Q, right? This is direct. The problem is you cannot know what is P and Q, the identification. It's hard-coded, right? You should know who you should expect, which is not very, trivial. So, and it can happen in symmetric or asymmetric, meaning you can send a message to process P, or in the asymmetric, you don't know necessarily who it's sending you. You just ask for, okay, just give me whatever I have, right? But still, you should send it to a process that you should know. This is still direct, right? And the indirect method is different because you should not know who is there. You talk about with mailboxes. So you assign a mailbox, which is the number that's unique, right? And then you establish your communication through that mailbox. So both the sender writes into that and then receiver. You don't know each other's IDs, but you communicate through that mailbox. It's similar to that shared memory, but it's not actually direct access. You are asking operating system to do this for you, and it's like very a protocol. There's a protocol, and so you address only the mailbox. So this, for example, can be an analogy for sockets. If you have done socket programming. And when you can create a mailbox and be the owner of it, and then the main receiver, you can destroy it as an owner. You can send or receive messages through a mailbox, and then basically, once it's established, you can read and write. You can have multiple readers. You can have multiple writers. How to deal with, conflicts. These are all the things that the OS should handle, and basically create this mechanism for other processes to, use and utilize, right? So. Again, if 3 processes share a mailbox and then 2 at the same time want to receive, what is to be done? So there are different solutions. One of them has a priority, or like a round robin, or they both receive it, or just have it random, arbitrarily receive it. Sender is notified who the receiver was. So P1 sends it and then gets to know, okay, P2 read it. So these are just the things that you need to handle as a communication between processes, right? And if you send a process, you can be blocked till it is received by your receiver. You can just continue. If you receive, you can just wait for a message to be sent to you, or again, just check and there's no mailbox for you, just continue running. These are, again, non-blocking and blocking methods of sending and receiving, right? And then that mailbox can have a capacity of 0. So if you want to send it you have to be blocked until someone wants to read it right there from you. This is called a 0 capacity, rendezvous. It can have a bounded capacity. If the mailbox is full, you cannot put the next message. You have to wait for it to someone read something, and then you can put it. It can have an unbounded capacity, which the OS should handle, and then just, sender never waits. You just put it there, OS handles, right? So this will be your next assignment for the next week, and just read it through the lectures slides. Will be uploaded today. If any questions, I'll be here. Yes. What? Hold on a sec. I will stop this.